Harvard just detonated the biggest controversy in space science. Their new 3I/Atlas alien arc hypothesis claims this isn't just an interstellar comet. It may be an engineered vault carrying life through the galaxy. Discovered racing into our solar system at over 130,000 miles per hour, 3I/Atlas now shows evidence scientists can't explain. Polarization readings that don't match dust or ice. A shell that looks more like shielding than rock. And with NASA and Harvard battling in public, the stakes couldn't be higher. Is this how humanity learns we're not alone, or are we witnessing the greatest misreading in scientific history? The real evidence is about to surface. On July 16, 2025, the scientific world erupted. Harvard's preprint, stamped with Avi Loeb's name, landed on our Arxiev and detonated across every major news network. Headlines screamed, "Alien Arc Hypothesis. Harvard astronomers say interstellar visitor could be engineered." In a matter of hours, Loeb's challenge to the scientific mainstream became the story. CNN cut to Loeb in his office, coolly declaring, "If this is artificial, the implications are dire. We have to consider every possibility, even the unsettling ones." The response was immediate and polarized. NASA's official statement, released within the day, called the alien technology idea nonsense and an insult to the discipline. Yet Loeb, already infamous for his Oumuamua claims, doubled down. On BBC World, he compared 3I/Atlas's odds-defying path to a blind date with a visitor from another star. He invoked the dark forest theory, warning, "If this object is what we think it could be, defensive measures might prove futile." The controversy spread like wildfire. Science podcasts, late-night shows, and social feeds exploded with debate. Some experts accused Loeb of chasing headlines, saying the data was thin and the risk of public panic real. Others, including his British collaborators at the Initiative for Interstellar Studies, argued that ignoring anomalies was the greater danger. The debate wasn't just academic, it was existential. Loeb's team insisted that the object's hyperbolic speed and trajectory, clocked at more than 130,000 miles per hour, demanded answers no natural comet could provide. NASA scientists countered with decades of cometary research, accusing Harvard of reckless speculation. Behind the scenes, the stakes were even higher. At Harvard, department meetings turned heated as faculty weighed the risks of backing Loeb's claim against the lure of scientific glory. Government advisors circulated classified memos on alien tech narratives and national space strategy. Aerospace contractors began lobbying for emergency intercept missions, with billions in funding riding on the outcome. In the glare of global attention, the question hung in the air: is this the first contact, or the greatest misreading in the history of science? The world demanded evidence, and the burden now fell on the data. On January 14, 2025, a team at Gemini North trained their polarimeter on 3I/Atlas and caught something that made even seasoned instrument scientists pause. The surface polarization, how the object scattered sunlight, shot beyond any value expected for comet dust or ice. In standard cometary physics, polarization is a fingerprint. Most comets, even interstellar ones, reflect light in predictable ways, with polarization peaking at modest angles and never straying far from established baselines. But the readings from 3I/Atlas defied those rules. The numbers were off the chart, as if the object's exterior wasn't made of loosely packed grains or frozen volatiles, but something denser, something engineered to withstand the relentless bombardment of cosmic radiation. The data passed every artifact test the team could devise. Calibration stars checked out, instrument drift was ruled out, and synthetic coma models, built from the best Maya theory simulations, could only explain part of the anomaly. The most extreme polarization clustered near the nucleus, not in the diffuse coma where dust jets dominate. For reference, natural comet grains, even the porous carbon-rich kind, rarely push polarization this high. The implication? A hardened, possibly continuous shell, not a fluffy agglomeration of ice and rock. A shell like this would be more than a curiosity. In deep space, radiation is lethal. Any cargo, biological, electronic or otherwise, would need armor to survive the centuries between stars. The Harvard team, bolstered by these findings, floated the shield hypothesis. If 3I/Atlas is an arc, the shell is its vault door. The argument gained traction as other observatories, including the Skalnate Pleso and NOT, reported similar polarization spikes. Each new dataset nudged the odds away from coincidence and toward intent. Skeptics, especially within NASA, pointed to the possibility of exotic dust or rare electrostatic effects. But the pattern held across instruments, across wavelengths, across nights. The shell wasn't just a statistical fluke, it was the first tangible sign that 3I/Atlas might not be a natural wanderer at all. As the debate raged, one fact remained: the shell was real, and no comet in recorded history had ever worn one quite like this. The first hint that 3I/Atlas was more than a shielded rock came not from its surface, but from its core. As the object crept closer to the Sun, spectroscopists at Harvard and their colleagues in South Africa tracked a series of green flashes erupting from the inner coma. At first, these emissions looked like textbook signatures, perhaps oxygen atoms fluorescing under solar UV, or faint traces of diatomic carbon. But the signal didn't fade as the comet rotated, or as its distance from the Sun changed. Instead, the green glow intensified in regular, almost mechanical pulses. Harvard's team, led by Dr. Hibbard, ran the spectra against every known cometary model. In standard chemistry, green emissions peak when carbon dioxide or C2 molecules break apart, releasing energy in a narrow band. But the intensity from 3I/Atlas overshot every prediction. The pulses came in discrete bursts, rising and falling with a rhythm that refused to match any natural process. For reference, the measured flux exceeded the maximum expected for even the most active solar system comets by more than a factor of 3, an order of magnitude that left even seasoned observers unsettled. Skeptics pointed to potential errors: atmospheric contamination, instrumental ghosts, or background noise masquerading as signal. The Harvard group countered with cross-instrument checks and stacked exposures from 3 continents. No matter the telescope or the night, the pulses returned. Each lasted just under 2 minutes, separated by intervals that seemed immune to the object's rotation or the shifting geometry of its tail. It was as if something inside was cycling on and off, like a reactor throttling its output. The implications rattled the community. If the glow was not chemical, then what was powering it? In the absence of robust carbon dioxide or C2 lines, the only explanations left were exotic, perhaps an engineered energy source, a non-thermal generator buried beneath the shell. For those who had spent careers modelling cometary outgassing, this was like hearing a diesel engine revving inside a snowball. The data did not fit. And if the object was generating its own power, then the next question was unavoidable. What was it protecting or sustaining within that shell? The search for answers turned inward, toward the heart of 3I/Atlas, as the world waited for the next anomaly to surface. On February 2nd, 2025, a Solar Orbiter Plasma team released their first batch of charged particle data from the vicinity of 3I/Atlas. What they found sent a ripple through the plasma physics community. The solar wind, the relentless stream of charged particles blasting out from the Sun, should have swept past the comet in a broad, turbulent wave, just as it does with every natural visitor. Instead, the data hinted at something stranger. Ions were bending around the object, as if encountering a magnetic bubble, a miniature shield floating through the void. For reference, most comets form a tail of ionized gas that trails behind, shaped by the solar wind's pressure and the outflow of vaporized ices. The interaction is chaotic, with field lines draped and tangled, never forming a true barrier. But the Solar Orbiter's instruments recorded narrow bands of deflection, angles sharper and more coherent than any plasma tail model could produce. The region of altered flow was tightly localized, hugging the nucleus instead of stretching into a diffuse fan. Field strength estimates, though indirect, suggested a pocket of magnetism at least twice as strong as the surrounding solar wind, and orders of magnitude more organized than the patchy magnetic fields measured at Halley's Comet or 67P/Churyumov-Gerasimenko. ESA's lead plasma analyst, Dr. Emilia Novak, summarized the anomaly in a terse memo. observed ion drift pattern inconsistent with standard draping, possible localized field or artificial shielding. She flagged the data for urgent peer review. Meanwhile, at NASA's Goddard Space Flight Center, a second team pored over the numbers, searching for instrument artifacts or solar wind fluctuations that might explain the readings. Their preliminary checks ruled out spurious calibration or background interference. The pattern persisted across multiple orbits and detector alignments. If the field was real, it implied a level of structure and persistence that natural comets simply don't achieve. For planetary scientists, this was like finding a compass needle spinning in the presence of a block of wood. The Harvard group seized on the finding, arguing that an interstellar arc, if it existed, would need such a shield to protect its cargo from the sun's fury. The debate over the shell had been about armor. Now, the conversation turned to active defense, to the possibility of a force field engineered for deep space survival. With every new dataset, the case for multi-system design grew bolder, and the line between comet and craft grew thinner. Buried beneath the scatter of cometary dust and the glare of solar light, the next anomaly arrived as a rhythm, steady, persistent, almost clinical. On March 5, 2025, the Vera Rubin Observatory's time series photometry registered brightness spikes from 3I/Atlas, repeating every 2 hours with the precision of a metronome. Most comets flicker and flare at random, their light curves sculpted by tumbling shapes or chaotic jets. But this was different. The pulses rose and fell in intervals too sharp, too regular to fit the usual cometary script. Rubin's analysts ran the numbers against every model in the playbook: rotation, jetting, outgassing, phase angle effects. None could replicate the crispness or the clockwork regularity. The spikes ignored the object's spin period and the shifting geometry of its coma. It was as if something deep inside was cycling on and off, indifferent to the chaos at its surface. The data drew attention from the James Webb Space Telescope imaging team, who had been tracking 3I/Atlas with infrared and optical sensors. Their logs recorded not just the heartbeat pulses, but faint, synchronized flickers in the surrounding dust, like echoes radiating from a central engine. For reference, the pulse interval held steady even as the object's brightness changed with distance from the sun. No natural comet on record had ever displayed such a strict periodicity, especially one unlinked to rotation or solar heating. The pattern was so regular that Webb's team compared it to life support cycles or environmental control systems, the kind engineered to sustain cargo through long, cold journeys. Just as the heartbeat anomaly was setting off debates, a second riddle appeared in the data. On March 18, 2025, ground-based telescopes and JWST's wide-field cameras reported pinpricks of light trailing 3I/Atlas. NASA's official line called them fragments, chunks broken off by outgassing or thermal stress. But the orbits told a different story. The companions moved in formation, their separations unwavering over days, their paths too precise for random debris. Harvard's theorists whispered about escorts, probes or monitoring devices perhaps, keeping watch over the arc. The orbital elements were cross-checked, and while some skeptics pointed to natural clustering, the odds of such alignment by chance were vanishingly small. For those fluent in celestial mechanics, this was like watching a flock of birds fly in perfect V, when every natural force should scatter them to the wind. Taken together, the heartbeat pulses and the disciplined procession of companions painted a picture that natural explanations struggled to contain. The data didn't just defy cometary convention, they suggested a choreography, deliberate and unyielding. And as more telescopes joined the hunt, the question sharpened. If this was not a rock, not a comet, then what kind of vessel leaves a trail of sentinels and a pulse that beats like a heart? Probability, in science, is a cold, unforgiving judge. When Harvard's team ran their Monte Carlo simulations, they found that only 5 out of every 100,000 random interstellar objects would ever thread the solar system's needle as 3I/Atlas did, brushing Mars's orbital corridor with such precision that the odds round down to 0.005%. Neil deGrasse Tyson, called in for a primetime segment, put it simply: either we're witnessing the greatest cosmic fluke in modern astronomy, or something is guiding this object with intent. Yet beneath the numbers, another anomaly surfaced. SETI's analysts, scouring the radio spectrum, flagged faint narrowband spikes that flickered near 3i/Atlas's passage. The signals, irregular, barely above the noise, refused to settle into any known astrophysical pattern. Officially, no one called them transmissions. Off the record, one SETI researcher described it as a whisper in a hurricane, too faint to trust, too persistent to ignore. Michio Kaku, ever the provocateur, speculated on air that if aliens ever sent an ark, they'd build in a failsafe, a beacon to phone home once it reached a target system. NASA's spokesperson dismissed the radio chatter as interference, but the story was out. Complicating matters, memories of Oumuamua's unexplained acceleration in 2017 returned to the headlines. Loeb, unyielding, drew the parallel in a congressional hearing. First the scout, now the carrier. We ignored the first messenger. Are we prepared to ignore the second? The committee chair pressed NASA's science chief for a response. The answer was measured, almost weary. We have no evidence of non-natural origin. Extraordinary claims require extraordinary proof. The divide between Harvard's bold hypothesis and NASA's institutional caution widened with every press cycle. Congressional panels demanded briefings, aerospace contractors lobbied for emergency intercept missions, public opinion fractured along lines of wonder and dread. In the data, nothing resolved. The Mars corridor odds, the radio spikes, the memory of a tumbling, accelerating visitor. Each fact sharpened the sense that certainty was slipping away. For now, the only consensus was uncertainty itself. On July 1st, 2025, astronomers confirmed 3i/Atlas as the third known interstellar object, moving at over 130,000 miles per hour. Harvard's release of the alien arc hypothesis cited 10 specific anomalies, from its unusually hard shell and pulsing green emissions to a localized magnetic shield and tightly grouped companion objects. Peer-reviewed data from Gemini North, ESA, and NASA confirmed that 3i/Atlas shows physical and energetic behaviors unlike any known comet. Yet, key questions remain. The composition of its shell is unconfirmed, radio signals lack official classification, and the true nature of its internal activity is still unknown. NASA and Harvard continue to debate the available evidence while public attention grows. What is clear? 3i/Atlas challenges our understanding of interstellar visitors. If future missions verify engineered features or signs of life, the discovery would reshape humanity's view of its place in the universe. For now, the archive remains open and the investigation continues.